Thanks very much. Thank you to the organizers for inviting me. This is the first Amplitudes conference I've attended in person. My background is more in string theory, but I hope I'll be able to tell this audience some things of interest. So, as the title of my talk suggests, I'll be telling you about aspects of collinear scattering in a class of self-dual gauge theories coupled to certain massless matter content. And largely, I'll be talking about a paper that appeared in December with my former PhD student, Victor Fernandez. Although all of this builds off of various earlier papers in collaboration with Kevin Costello that I'll mention as time goes on. I'll have to suppress some of kind of the formalism in the background in view of time. But Kevin gave a review talk at last year's Amplitudes, which is recorded, and to which you can refer for more details if you need to. Or, of course, come talk to me afterwards if you'd like to hear more. Okay, so here essentially is going to be the one slide summary of everything I'm going to tell you about today, and then I'll unpack it in the remainder of the talk. So I'm going to be studying a class of 4D quantum field theories, which are integrable, not only classically, but also at the quantum level. They're not necessarily supersymmetric, although they can be. I'll mostly focus on the non-supersymmetric examples in this talk. And as you might expect of a 4D quantum field theory that enjoys integrability, they don't have non-trivial scattering amplitudes on flat backgrounds, but nonetheless, they turn out to have interesting and non-zero form factors. So when I talk about scattering in these theories, I'll always mean form factors, so scattering in the presence of a local operator insertion. In particular, these theories are extremely simple, and that simplicity descends to properties of their form factors. In particular, the form factors have no branch cuts, and the poles structure, the analyticity is very constrained. They only have poles in certain holomorphic collinear limits, but no other singularities. Nonetheless, this non-trivial collinear scattering persists to arbitrary loop orders, so I'll use h-bar to index the loop order that I'm interested in. And so non-trivial collinear splitting functions emerge to arbitrary loop order for any form factor that I want to compute. And the nice thing about these theories, well, as you might expect from all of the special properties I've just outlined, is that, in fact, you can obtain analytic expressions for these form factors. In particular, they're completely determined by these collinear limits. And so you can successively reduce an L-loop form factor computation to lower point and lower loop form factor computations, all of which are recursively determined by various splitting. And the kind of special and perhaps remarkable thing about these particular theories is that one way to do this, which follows from their nice integrability properties, is that you can use 2D CFT techniques. That's more my background, so I'll be taking the perspective of a 2D conformal field theorist to get the results that I'm interested in, but they have nice four-dimensional translations. In particular, the 2D CFT that plays a role in these theories are what are called 2D chiral algebras. So you should think of them as two-dimensional, purely holomorphic, or purely chiral conformal field theories. So very, very simple. So as I said, the particular theories for which all of this works are self-dual Yang-Mills, coupled to special choices of matter content, which is dictated from a twistorial origin to these theories. I'll largely suppress all of the twistor space formalism in this talk, but one way to think about the integrability of these 4D theories is that they have nice uplifts to holomorphic quantum field theories that are also ordinary local quantum field theories on twistor space. So there's a six-dimensional or a twistor space origin for a lot of the formulas and the constructions that I'll talk about. Again, I'll largely suppress it for this talk, but if you want more details, feel free to ask me. Okay. Now, self-dual Yang-Mills, although I'm forced to couple it to some special choices of massless matter that I can't choose freely. But nonetheless, I think a nice thing about these gauge theories is that self-dual gauge theory, as is known by probably all of you in this audience, captures certain simple helicity amplitudes or form factors in ordinary gauge theory, and things that have, say, at least mostly plus external, mostly positive external helicity states, or perhaps with a few negative helicity states, depending on what we compute. So one way to kind of think about these, the results of this talk is that thanks to kind of 2D CFT technology, there's really a very small subsector of massless QCD coupled to special matter content, so not NF equals 6, that's exactly solvable at the perturbative level. You can just know everything about their form factors, and the singularity structure is extremely constrained. Now, whether or not one can push these things to more interesting theories with more generic choices of matter is the subject of a little bit of existing work and more work in progress. So stay tuned. Okay, so that was the one-slide summary of everything that I'm going to tell you about. In the rest of the talk, the plan will be for me to introduce the 4D theories in a bit more detail. And then I'll explain how 2D chiral CFTs, I'll refer to them as 2D chiral algebras, are sufficient to govern all of the scattering in these theories, again, by means of holomorphic collinear limits, which is really all these theories have. And in the recent work with my former student, Victor, we obtained all loop expressions for these holomorphic collinear splitting functions. And then I'll conclude. All right, so what are the theories that I'm interested in? I already told you what they are. They're self-dual gauge theory, self-dual Yang-Mills, coupled to special choices of massless matter content. So let me just briefly review self-dual Yang-Mills and tell you precisely which matter content I'm allowed to add for this program to work. Okay, so self-dual Yang-Mills, something again probably familiar to many of you in the audience. It has a nice Lagrangian formulation due to Chalmers and Siegel from many years ago. One can write down a BF type action, where B is an anti-self-dual two-form field, and F minus here denotes the anti-self-dual part of the gauge field strength. So morally speaking, or well, more than morally speaking, you should think of B as encoding in my conventions negative helicity gluons and A encoding on shell positive helicity gluons. So they appear quite asymmetrically in BF theory, as you might expect. Now, this action, again, it's quite simple. There's a propagator that takes A to B, or plus to minus, and I have these little arrows to denote the flow of helicity and momentum in these diagrams. And there's a minus plus plus vertex, but not its parity conjugate, not all the vertices that you have in ordinary Yang-Mills theory, of course. And if you sit down in self-dual Yang-Mills theory by itself and you try to draw kind of all the non-trivial Feynman diagrams that you might wish to try and compute in these theories, you'll find that the scattering content of self-dual Yang-Mills by itself is quite poor. It's one loop exact. And in fact, the only thing you can draw is a one loop all plus amplitude. And I've just drawn the one loop 4-point diagram here. And that expression, of course, has been computed for a long time. It's been known for many years. And likewise, the collinear splitting function that can contribute to this amplitude has also been computed and known for a long time. Now, BF theory can be deformed to Yang-Mills with the addition of a term proportional to trace B squared in the Lagrangian. So you get something that's perturbatively equivalent to ordinary Yang-Mills. There's a non-trivial theta angle that won't concern me today because I'll purely be working in perturbation theory. And so one can, of course, consider various amplitudes, various helicity amplitudes in Yang-Mills in a perturbative expansion around the self-dual center. In particular, so here's my full action. If I just work to first order, then from a diagrammatic perspective, I've allowed myself to add an extra vertex that can contribute to these diagrams, where this little dashed circle denotes my trace B squared insertion. So with the addition of this, I can draw a few more diagrams. So if I restrict myself to just a single trace B squared insertion, kind of the first simplest thing that I can start to compute, there's a few diagrams that I have access to. In other words, there are certain form factors in self-dual Yang-Mills with a single insertion of the operator trace B squared that essentially compute certain simple helicity amplitudes in gauge theory. In particular, with one trace B squared, I can compute tree-level MHV scattering, one loop one minus scattering, or two loop all plus scattering. And so here's the two loop example where that trace B squared vertex is in the middle there. I borrowed this picture from Kevin's talk last year, and I can draw similar pictures for these other two cases. Okay, so form factors in self-dual gauge theory compute certain helicity amplitudes in Yang-Mills. More generally, I can consider other local operator insertions. Nothing's stopping me from doing that. And some of those things are non-zero even at higher loop order and are non-trivial. For example, a trace B to the n type operator on shell is nothing but various insertions of the anti-self-dual part of the gauge field. So I can compute some helicity form factors in Yang-Mills this way. And just to give an example, a trace B cube type form factor has a non-trivial 3-loop diagram. Okay. So those are all things that I can just study in gauge theory. That's just a purely 4-dimensional statement if you want to start computing some of these form factors. What I want to emphasize is that all of these amplitudes or form factors more generally have non-vanishing contributions to certain holomorphic collinear limits. That's true at arbitrary loop order, and they all contribute to these general form factors in this theory. So here schematically, you can kind of imagine that maybe I have some totally other diagram here, where the blob is. Perhaps I have some other complicated thing. And I might want to study the contribution of this general diagram or the contribution of a collinear limit to that general diagram by taking these two positive helicity gluons very close to one another. And it turns out that there's kind of what might be called a non-factorizing contribution to this process, where these two, the J's, you should think of as positive helicity gluons, two J's come together. There's some product of three negative helicity gluons denoted by J tilde here. I've written this in a 2D CFT way in anticipation of how I can compute this thing later. And there is some non-zero splitting function at 3 loops with an undetermined coefficient. And that's just one example. I've just given you the 3-loop example because I've drawn kind of the corresponding diagram, essentially. But again, there's non-trivial things at all loop order. And the important thing that I want to emphasize, or kind of the punchline of today's talk, is that these expressions, including this undetermined coefficient b, it's complicated, but now it's known. And not just this 3-loop contribution, but all holomorphic collinear functions to arbitrary loop order. All right. So as I said, for me, the important property that lets all of this stuff hang together is the integrability of the 4D quantum field theories that I'm interested in. Now, self-dual Yang-Mills by itself, as many of you probably know, is classically integrable. That's an old story. There's many different avatars of this statement that are all equivalent to one another. For example, there is an infinite tower of conserved currents classically that lets you solve it. And it has a local twistor space uplift due to Ward that, in fact, is also a BF theory. It's what's called a holomorphic BF theory. But as has been noticed by many people for a long time, these conserved currents classically fail to be conserved quantum mechanically. And the non-conservation can be attributed to the non-zero one-loop amplitude in self-dual Yang-Mills that we talked about earlier. So if I'm interested in integrable theories, and obviously I am for my own reasons, then what I'd like to do is cancel off that one loop all plus diagram, restore integrability of the conserved currents, and then use these conserved currents to bootstrap the computation of the form factors in these theories. Now, a nice feature of, say, the twistor space uplift, or the interpretation on twistor space, is that this one loop all plus diagram lifts it lifts to a one loop diagram in 6 dimensions. But in 6 dimensions, I interpret the same diagram as a gauge anomaly of the holomorphic 6-dimensional BF theory on twistor space. Now, holomorphic gauge theories essentially are like chiral things, so they can and they do suffer gauge anomalies, and this is the diagram encoding that. So essentially, the obstruction for these 4D theories to be integrable at the quantum level can be viewed as the non-existence, by means of this local gauge anomaly, of their twistorial uplift. And recently, Costello proposed that, in fact, this thing that I just said in words is true. And so it motivates us to cancel the gauge anomaly on twistor space to restore integrability. And there are various ways to do that. Supersymmetrization is one way, but it's not the way I'll focus on today. There's some Lie algebraic condition that one has to satisfy to do it, with various choices that depend on your gauge algebra and particular representations that you might want to add to your theory. So now I'm finally going to, as I said, add some judicious massless matter that satisfies relations like this, just to cancel the gauge anomaly of the twistor space uplift and restore the integrability of this theory. Now, as I said, there's various ways to do this in various combinations. For certain representations, just ordinary fermionic matter will do the job. And there's also more exotic things like a Green-Schwarz type mechanism. The first mechanisms were studied in these papers. Roland, who's here and we'll talk on Thursday, also found some new interesting examples as well. And I'm going to study, essentially in the paper from December, we can kind of treat all of these examples at once. So everything I'm going to say is good for any way you might wish to cancel the anomaly. But I'll tell you some specific examples. So just to kind of orient you, what are some examples of the kinds of massless matter content I need to add to make these theories integrable or rational? For example, for SUN self-dual Yang-Mills, written here in terms of Weil fermions, one can add 8 copies of the fundamental and anti-fundamental, as well as the 2-index anti-symmetric tensor representations. And kind of the simplest Examples in this family are SU2 with NF equals 8 Dirac fermions and SU3 with NF equals 9. Because in SU2, there is no such representation here, and in SU3, they just combine to give me another copy of the fundamental and antifundamental. So these are the simplest examples to keep in mind. There's also other interesting things one can do if you include this Green-Schwarz scalar that I mentioned earlier. I'll call it the axion sometimes, not because it's an ordinary axion, but it turns out to couple to F wedge F in 4 dimensions. Don't worry about the details. But if you add this thing, you can also study SUN with N flavors. So there's some more games one can play. And of course, there's other examples here. And talk to Roland if you want even more. OK, so those are the theories that I'm going to be interested in. For example, SU3 with NF equals 9. And now I have to tell you about the 2D chiral CFTs that control the form factors in these theories. OK, so what I've just done is guaranteed that I have some infinite number of conserved currents, even at the quantum level. And adding matter, of course, will deform the OPE, the operator algebra that was inherent in these currents, in general, order by order in H bar. I've certainly added matter generators. I've deformed the OPE. In terms of notation, I'll always, as is natural from a twistor space point of view, work with complexified momenta. So here's my usual momenta and spinor helicity indices, lambda, lambda tilde. For me, I will not demand that lambda tilde is the complex conjugate of lambda. I'll keep them independent of one another. And so I'll study a generalization of ordinary collinear limits, which are called holomorphic collinear limits, where the angle brackets ij go to 0, but the square brackets can remain fixed. So in some nice affine coordinates, I'll write lambda as 1 comma z, and I'll leave lambda tilde arbitrary, so that these angle brackets equivalently can be thought of as kind of the difference between two z's. And I do that to make contact with the 2D CFT notation. Ultimately, I'm going to have some chiral CFT, and the OPE limit of currents or operators in the CFT as their insertion locations approach each other are going to be precisely these holomorphic collinear limits I just mentioned. So OPEs in the 2D chiral CFT, which is the way in which I will reorganize these currents, are holomorphic collinear limits in these 4D gauge theories. OK, so again, z is like a 2D holomorphic coordinate, and I'm starting to make some of the 2D chiral algebra structure manifest. And it works because I can treat lambda and lambda tilde essentially on a different footing. Again, as the twistor space aficionado is probably expected already. All right. So in a theorem we proved in 2022, the 2D chiral algebra exists, and in particular is consistent, i.e. is associative. It's a well-defined ordinary local chiral CFT if the stressorial uplift exists. And moreover, form factors in the 4D theories I've been talking about, we proved are nothing but correlation functions in this 2D chiral CFT. They have the properties that I said earlier in the talk, so I won't repeat them in view of time. But in particular, because if you have the OPE of this chiral CFT to arbitrary loop order, then for any form factor you might want to compute at L loops, if you know the OPE, you can just start applying these OPE limits or holomorphic collinear limits and gradually reducing the problem in terms of collinear splitting functions times lower loop or lower point form factors, and you successively simplify the problem in this way until you get down to something like a basic 2 or 3 point function. And those are typically determined by symmetry. And we call this method of computing things the chiral algebra bootstrap, and there's more details in our earlier papers as well. And another nice feature of these chiral CFT computations is that if you compute, say, a 4-point form factor, you can actually use induction to pretty easily give you an n-point form factor. All right, so here's the one-line summary. Operators in the CFT are nothing but ordinary on-shell scattering states in 4D, their usual momentum eigenstates, and the OPEs are these collinear limits. And again, this might have been apparent to the twistor space people, but the C coordinate can be usefully thought of as parametrizing the celestial sphere. And so if you take the chiral algebra OP, or the chiral CFT OPE that I'll present to you, if you set kind of the generators corresponding to the massless matter to 0, and if you take the classical limit, you'll recover what's called the celestial chiral algebra that's been studied in other contexts by other folks. All right, so we have a big chiral CFT. Here's the generators. There's a bunch of symmetries and a bunch of quantum numbers. I'm, of course, not going to tell you all the details. essentially all of these things come from twistor space because the twistor space theory has a tremendous amount of symmetry. In particular, I have the complexified Lorentz group acting as Mobius transformations on Z and also as rotations of those lambda tildes. So those are in the game. There's rescaling of four-dimensional spacetime. There's some other symmetries associated to the twistor Lagrangian. And I can just enumerate all of the quantum numbers and symmetries for all of my chiral algebra generators. And that, it turns out, will enable me to uniquely fix the form of the operator product expansion to all loop order. So just for notation, J denotes a positive helicity gluon, J tilde a negative helicity gluon, matter is M and M tilde. These are the Green-Schwarz scalars, not too important. But so here I've just written my momentum eigenstates in my chiral algebra notation. So here's JA, a positive helicity gluon, A is my adjoint index, lambda tilde and lambda are present, momentum eigenstates. And it's often convenient to also expand these in terms of powers of the lambda tilde components, just because it's more convenient to write the OPEs in terms of these Taylor components. In the literature, they're sometimes called conformally soft modes, but in a form factor, if I expand this in terms of the J and M's, only a finite number of the J and M's contribute. All right. Now, as I said, if I compute a form factor, say with a single trace B squared insertion, there's these three options, and we computed them with chiral CFT technology. Just to show you a formula, here's the one loop one minus answer, and it is indeed a nice rational answer. And the two loop all plus answer was also verified for 4 points, although I stress again the chiral CFT answer computation gives you the endpoint answer. At 4 points, Dixon and Morales verified that this is the right answer with more traditional methods. So indeed, this approach works. And then the punchline of the talk is, well, if I want to compute things to general loop order, say these trace B to the n form factors at n loops, I need the OPE to n loop order. And it turns out that associativity and all of these symmetries I mentioned are enough to completely solve the problem and fix the OPEs, and that's the hard work that we did. So at one loop, the OPE includes the familiar one loop splitting function of self-dual Yang-Mills. That's a subset of the splitting functions in ordinary Yang-Mills. But there's additional terms coming from the twistor space anomaly cancellation condition or from matter exchange. And again, the conjecture was that you could solve the problem and compute the OPE to arbitrary loop order. It wasn't clear a priori that this was possible to do in practical terms, although we conjectured that it would be possible. Maybe these things are symmetric enough that you can actually do it, and you can do it. So again, here's the recipe. We determined the general form of the OPE corrections, essentially by requiring equivariance of the OPE under all of those symmetries in the table that I posted on the previous slide. And there's a bunch of undetermined numerical coefficients that you have to solve for. But just demanding associativity of the CFT, equivalently Jacobi identities of the mode algebra, is actually enough to fix these things completely. And so then one just has to do a lot of hard work. So I'll just end by showing you a few formulas just to maybe reassure you that we actually did the hard work of solving these things, and then I'll conclude because I'm out of time. So for example, here's just the higher loop OPE for the J tilde J operators. So these are the 1 minus 1 plus collinear splitting functions. You get a bunch of J tildes on the right-hand side. However many you have depends on what loop order you're at. So there's an H bar to the M indexing everything here. And there's some undetermined coefficient F of M, which has a bunch of gauge indices and some numerical dependence. Here are just some other OPEs. What I want to stress is that the OPEs, not just the ones I presented, but everything, they only have single and double poles. So there's only 1 over angle brackets or 1 over angle brackets squared poles in these theories. That's all you can have. Moreover, all of the OPE coefficients can actually be solved in terms of F, and then F we can actually determine in terms of a nice recursive equation. So here I've just kind of split off the gauge dependence in a kind of standard way. Here are some OPE coefficients in terms of F. There's just some numerical factors. And then F itself has a recursion relation that you can plug into Mathematica and just start generating things for. So F at M loops is determined by a sum of products, F of n minus 1 loops times F at 1 loop. And F at 1 loop we computed in 2 different ways. Again, they're ugly formulas with a bunch of factorials, but you can plug them into Mathematica and just kind of go. There's also a closed form expression, but it's kind of formidable, so I'm not going to show that to you. I think the recursion relation is something friendlier to plug into your computer, and again, just go. All right, so I'm out of time. So I've shown that chiral algebra OPEs are equivalent to, or at least I've argued that they're equivalent to holomorphic collinear scattering in a special class of 4D theories, and we've determined them at arbitrary loop order. So this effectively solves a very small subsector of massless QCD with very special matter content. Much more has to be done in the future. For example, what about form factors with multiple local operator insertions? And I'll just note these two papers by Dixon Morales and Anthony Morales to appear that uses these rational theories to compute some things for more interesting theories. And I'm done.